Now that we've got a lot of conversions under our belt, let's go ahead and put all these concepts together. Let's do some stoichiometry involving solution chemistry. So, in solution stoich, you're going to use your moles as your common ground. This is just like regular stoich. If you can find the moles of your known solution, you can do anything. So, find the moles of your known solution and convert to the unit of your unknown. Ask yourself, what am I trying to determine? And this little chart may or may not help you, but everyone represents a conversion factor. So, density. Density is a conversion factor. Molar mass, conversion factor. Molarity, conversion factor. Avogadro's number, conversion factor. Stoichiometry, conversion factor. Density is your mass over your volume. Molar mass is the mass of 1 mole of material, so the mass in grams of 1 mole of that material. Molarity is the moles of solute over liters of solution. Avogadro's number, that tells me that every mole of something has 6.022 times 10^23 of that thing. And your stoichiometric factors, again, that can come from the formulas themselves or from a balanced chemical equation. So with just these conversions, you can do all kinds of things. Some of the different reactions we will talk about. This is not an exhaustive list, okay? But we'll talk about precipitation reactions, which are also known as double replacement or DR reactions. We'll talk about salt hydrolysis, which is where you have a basic species that steals protons from water, or acidic species that donate protons to water. Neutralization reactions. This is another form of a double replacement reaction, but weak bases accept protons and acids donate protons. Redox reactions, double replacement. So, like number one, except instead of producing a solid, which is a precipitate, it results in a gas being produced. We have single replacement reactions, or SR. We're going to look at metals reacting with water and nonmetals, metal oxides, I apologize, metal oxides reacting with water and nonmetal oxides reacting with water, and what they're going to form. One will form an acid, one will form a base. We're going to spend some more time on combustion. We've already learned combustion. So remember, combustion is where you have the reactant plus O2 gives you CO2 plus water. Assuming that your reactants here are only carbon, hydrogen, or carbon, hydrogen, oxygen. Synthesis is where you take more than one reactant and make one product, or generally speaking, less products. And the decomposition reaction is where you take one or two things and you decompose into more product. So again, there are additional categories that are useful as we try to predict the possible products. The final authority here is always experimentation. Rules are made after many observations have been shown, and we can see the patterns that are coming through. We can use these patterns to predict future reactions. So let's spend a little more time talking about a precipitation reaction. What is it? A precipitation reaction is a forming where a solid forms from a double displacement reaction. So double displacement is where you swap ionic partners. I have two soluble ionic compounds, and they react to form some type of insoluble product. The driving force of this reaction, the whole reason it occurs, is the insolubility of that product formed. So the fact that the product form is insoluble is what drives this reaction forward. So you should have your solubility rules memorized. If you don't, it's going to make this very difficult. So get them memorized. You're going to use them to predict if an ionic compound is soluble or insoluble, and then use to predict if a precipitation reaction will occur. So let's look at the picture here. Okay, double displacement reactions. You inspect the possible products that could be formed from combinations of the ions in solution. And you're going to refer to your memorized solubility rules to do it. And then you ask yourself, will an insoluble product form? If an insoluble product forms, again, insoluble means solid. So that is your precipitate. The picture here shows what's happening a little bit better, but you guys should also be drawing your own mental pictures here. I have two reactants here that I'm going to mix together. In my first, I have Ki, potassium iodide. I know potassium iodide is a strong electrolyte and is soluble in water because potassium is an alkali metal, it's a group 1 metal, and when it's in its cation form or ionic form, it is always soluble. So I have some potassium ions floating around and some iodide ions floating around. My other reactant is lead 2 nitrate. I know that this is also soluble because although lead is not always soluble, nitrate salts are always soluble. So I know this will be Pb2 plus and some nitrates floating around. And for every one Pb2 plus, I will have 2 nitrates floating around. So I'm going to go ahead and mix these two things in solution. Okay. In one beaker, I have one, in the other, I have another. But I go ahead and I just mix the solutions together. When you mix these solutions together, I want you to think about who wants to hang out where. Does a cation and a cation want to hang out together? No, they really don't. They have the same charges. They're not attracted to one another. Does an anion want to hang out with an anion? Also, no. They have the same charge. They don't want to be together. Opposite charges attract. So, does the lead want to hang out with the nitrate? Well, clearly not. It already left the nitrate behind. That's why it was soluble. Does the lead want to hang out with the iodide? You know what? It does. This is one of my insoluble products. Why do I know that? Because I know my solubility rules. What about potassium nitrate? No, if they have solvent there, they're not going to do anything. They're going to just keep floating around as potassium ions and nitrate ions because, again, they are completely soluble in solution. They don't actually want to pair up, so they just keep moving around the solution. But this lead to iodide, oh, 100%. If lead finds two iodine molecules or two iodide molecules, it is going to form PbI2 solid. So my products here, you take the cation of one and the anion of the other, KNO3, and you ask yourself, is that going to be soluble or insoluble? That's going to be soluble because potassium ions are always soluble, potassium salts always soluble, and nitrate salts always soluble. And then you take the cation of the other with the anion of the other. That's why you're swapping partners. And PbI2, and that will form a solid. And that's what we see in the picture over here as well. So you can see here the K plus and the NO3 minus floating around in solution. Sorry, up here. Let's do it up here. I forgot the K plus. Let's start where we started. K plus and I minus just floating around in solution. They don't want to have anything to do with each other. They let go of each other because they're stabilized by water. The lead 2 plus forming 2 nitrates for every 1 lead 2 plus floating around in water. When you form that solid, though, the K plus, the potassium ion, and the nitrate ions keep floating around. But the moment the lead can find 2 iodide ions, it's going to form this 3D crystal structure because it's an ionic compound. And to you guys, it looks like this yellow solid. But at the molecular view, we see what's really happening. Again, I can predict this though, because I know my solubility rules, and I know that this formation of this is the driving force of the reaction. The formation of my insoluble salt. Next up, we have salt hydrolysis reactions. A salt hydrolysis reaction is where you have a salt that's causing a solution to be acidic or basic. So basically, you have a cation portion or an anion portion of your salt in solution that's acting as an acid or a base. So you can see here, what do I mean by that? Acts as an acid or a base. Well, again, remember acids, the Arrhenius acid, definition of Arrhenius acid is production of H3O+. It does this by donating a proton to water, forming H3O+. So here, we can see NH4+, which you guys know as ammonium ion. Acts like an acid by donating its proton, donating its extra proton to water. And so by donating it, it's forming H3O+. It's acting as an acid. In this case, water is accepting that proton, so water is acting as a base. So again, this is acting as your acid. This is acting as your base. But this will cause your solution to be acidic. We've also got, so you can have some cations if they have an extra proton. This often happens if you have a nitrogen-containing compound, and that nitrogen-containing compound has a positive charge to it. So ammonium is the perfect example for this. That is when it will act as an acid in solution, donating the proton to water, forming H3O+, which causes the solution to be acidic. You could also have a species, though, that acts like a base by accepting a proton. F- is a great example of this, the fluoride ion. F- acts like a base by accepting a proton. And again, just to reemphasize what we mean by proton, if you have a hydrogen atom, remember it has one proton and one electron. If I form a hydrogen ion, if I form the positive charged ion, it only has one proton left. Its one electron has been taken away. And that's why we call it a proton. Because that's all that's left in its nucleus, or all that's left in its atom besides its neutrons, is the proton in its nucleus. So we see here F- can accept a proton, forming HF and hydroxide. So the F- here is acting as a base, forming hydroxide. The formation of hydroxide is the Arrhenius definition of a base. Here, water is acting as the acid. So note the little box down here in the spring semester. So in Chem 2, you will need to predict which ions react with water. But so when it says spring, it means Chem 2. But for this semester, for Chem 1, you will be told whether it's acting as an acid or a base, but then you should be able to predict the product. So if I tell you you have ammonium in solution and ammonium's acting as an acid, you should know that it's donating that proton to form H3O+, leaving behind the original species without that proton. If I tell you you have something like F- and it's acting like a base, bases accept protons, so you should know that that means that you are going to be accepting that proton, forming hydroxide, but that original anion has that extra proton now. We also have acid-base reactions. Remember, an acid is defined as a substance that produces H+, which technically speaking, H3O+ ions in solution. We say H+ for simplicity, but really it's donating that proton to water, so it's really forming hydronium. A base is a substance that produces hydroxide ions in solution. Strong acids and bases completely ionize an aqueous solution. And to emphasize that, we use a single-headed arrow, meaning there's no return. It's going one direction only. Weak acids and bases only partially ionize in solution, so we use what we call your equilibrium arrows. Meaning the reaction can go forwards and backwards. And we spend a lot more time on this in Chem 2. You should be able to write and balance acid-base reactions. So looking a little more closely, your acids are ionizing in water to form H plus to give up those protons. Acids want to donate the proton to a water molecule. So the proton from the acid molecule is donated to a water molecule to form hydronium. Notice again, though, and I've said this before, but I'll say it many times in the future. As chemists, we use H plus and H3O plus interchangeably. You have to understand that H3O plus is what is really in solution. This is our shorthand. Okay? You have to understand that. Even more precisely than that, each H plus is usually surrounded by 6 water molecules, but we're going to use H plus or H3O plus abbreviations because that's what makes most sense for people. Really, it is the surrounding idea by the water molecules. We spend more time on this idea in Chem 2, the stabilization of the ions in Chem 2. But you can see here that HF is a weak acid. It's not one of the ones I have memorized, so it is a weak acid. So it dissociates to form some protons and some fluoride ions, but this equilibrium arrow here means that this reaction can go back and forth. So an HF can split apart to form an H plus and an F minus, but if an F minus ion happens to find an H plus in solution, it can also recombine to form HF. And again, you can also write that as HF plus water, giving you F minus and hydronium. As long as you're balancing the reaction, I'm not picky on which way you write it, okay? But if you write water in the reaction, you have to write H3O plus. If you do not write water, you have to write H plus. Bases dissociate in water to form hydroxide ions. So bases like ammonia, NH3, which you don't have to technically have memorized yet, but it would be easier on your life if you just went ahead and memorized ammonia is NH3. They do not contain hydroxide ions, but they form hydroxide ions in solution by taking the by pulling that proton off of a water molecule. So if you've got a water molecule and the ammonia comes along and it steals that proton, so now what it's got down here is the NH4. This species now has a plus charge to it because it just stole the proton. All that's left behind, the oxygen keeps the electrons, and what's left behind is a hydroxide ion. So bases like ammonia, nitrogen-containing compounds, are able to do this because they steal a proton from water, forming the hydroxide ion. The proton attaches to the nitrogen because that nitrogen has a lone pair of electrons that allow it to attach. So again, my original ammonia looked like this with that lone pair right here. It's that lone pair of electrons on that nitrogen that allow it to steal that proton from water and then in turn form hydroxide. So neutralization reactions. Okay. One more small part about bases. Again, you can see the reaction right here with weak bases. Your strong bases just dissociate, and you guys should be comfortable writing out these reactions. If I have something like calcium hydroxide in water, it is a strong base. So it is a single-headed arrow. It forms calcium ions. And notice for every one calcium ion formed, it forms 2 moles of hydroxide ions. So it's still forming the hydroxide. We just have double of it because we have 2 hydroxides here, okay? So neutralization reactions. The dissolved ions are going to rearrange in solution. 1 mole of H plus reacts with 1 mole of hydroxide to form 1 mole of water. The salt is the formula of the neutral compound that's formed from the remaining spectator ions. In solution, they exist as ions. If I remove the water from the solution, or if I remove all the water, remove all your solvent, they're going to form salt. So let's talk through the first problem, and then we'll do the second one as well. The first one, I've got hydrochloric acid. I know my naming rules. I know hydro in ic means it came from ide. So this came from chloride, which is Cl minus, and it's the acid form, so I give it enough protons to make it neutral. I've got HCl. I've got sodium hydroxide. I know sodium is Na plus, hydroxide is OH minus. It's a 1-to-1 ratio, NaOH. Now your neutralization reactions are a double displacement reaction. So the cation from one combines with the anion of the other. Cation from one with the anion of the other. When I do that, I get H2O, and then I get NaCl. I know my solubility rules though, and I know NaCl is soluble in solution, so that would just stay floating around as ions. So what does this actually look like? If I had the system, let's say originally I put them in 2 sides of a container and I've split them up. One side I have my H plus ions and my Cl minus ions. The other side would have my Na plus and my OH minus. Okay, and again, what's not pictured here, the white space is all of the water. The moment I allow these to mix, they start mixing. The sodium comes along and it's like, oh, you got chloride, that's cool, but I'm gonna keep floating around. I don't really want to hang out yet. Like we can be associated, but I'm not gonna hang out. I'm not gonna pair up. But the proton finds the hydroxide, and every proton and hydroxide that pair up form one water molecule. So I have in this picture here, two additional water molecules being formed. I say additional because, again, it's already in water. I'm just forming more of it. But let's say I heat this up and boil off all of the water. If there's no water present, then I will pull out solid NaCl. If you ever, most people have tried this at one point in their lives, taken some table salt, put it in water, and it appears to disappear. But if you let the water evaporate away or you boil it away, the salt comes back. The salt never disappeared, it just formed ions in solution, and now we have the actual ionic compound back when the solvent is gone. The driving force of a neutralization reaction is the formation of water. It releases water, it forms water, and what it's not stating is it also releases heat. But that is another chapter. So we've got the first reaction. Let's do the second reaction down here. Let me erase this so we can fit this in here. Oxalic acid. So again, I don't have any hydro in front, so ic acid. Ic comes from 8. So oxalate is one of my polyatomics I should know. I know oxalate is C2O4 2 minus. So in order to make an acid here, I need to give it enough protons to make it neutral. So H2C2O4. Barium hydroxide. Barium is an alkaline earth metal, group 2, so it has a +2 charge, which means that it will have 2 hydroxides for every 1 barium. Double displacement reaction. So my cation from one with my anion from another, my cation from one with my anion from another. And I see what I form here is 2 moles of water, because I have to balance my reaction, and then barium oxalate. And barium oxalate is soluble in water. So let's apply a little bit what we've learned. What mass in grams of sodium bicarbonate, NaHCl3, is required to neutralize 100 mils of a 0.35 molar H2SO4 solution? Well, let's think about our balance reaction here. I've got NaHCl3, which is a sodium bicarbonate. I am reacting this with H2SO4, which is sulfuric acid. Again, cation of one, anion of the other. That's going to form sodium sulfate. Sodium is a +1 charge, so I'm going to need 2 of them to pair up with my sulfate. Cation of one, anion of the other. This actually forms H2CO3. But we're going to talk about this reaction, and we're going to see that this is a double displacement gas evolution reaction. So this will actually form Na2SO4, H2CO3, or sorry, not H2CO3, H2O, and CO2. We're not there yet, but you will see this coming about. So whenever you form H2CO3, and I'll talk about how I know it was H2CO3 in just a sec, but whenever you form carbonic acid, H2CO3, aqueous, it further decomposes to form water and CO2. Sorry, I'm trying to turn off that function on my iPad. There it goes. The reason I knew it was H2CO3, I'm gonna have to balance in a sec, but I had H2 here. I had 2 moles of H plus and then an HCO3 minus. It can only pick up 1 proton. That's how I know it's forming H2CO3, not something like H3CO3. It can't do that. The carbonate ion itself, CO3 2 minus, only has a 2 minus charge, so it can only have 2 protons to it. But now I need to balance it. Let's see, I need 2 sodium, so let me go ahead and put a 2 in front of there. That's going to cause me to need 2 carbonates, so let me put a 2 in front of here. I'll balance these out in a sec. Now I have 2 carbons, 6 oxygens, 2 nitrogens. I have 1 sulfate, and I have 2 hydrogens here and 2 here. I have 4 hydrogens, so it is balanced. So this will further break down. This will stay this, but this will break down into 2 moles of water and 2 moles of CO2. Because again, if you add this up, I have four hydrogens here, my oxygens here, 2 oxygens from my water, 4 more from my CO2, and then 2 carbons here. So it is, in fact, balanced. I need to realize that this is not an actual product. Okay, these down here are the actual products. I'm going to go ahead and erase those and move my actual products up. Move this over just so that we use the right stoich in just a minute. Again, it's called the double displacement gas evolution reaction. We will talk about them soon. Okay, so now that I've got a balanced reaction, I can actually solve the question. What mass in grams of sodium bicarbonate is required to neutralize all of this acid? So I want to know the number of grams of NaHCO3. I'm trying to neutralize a 0.350 molar solution of sulfuric acid, and I have an entire liter of it. I have 1,000 mils. So it doesn't matter what number you start with, but I'm going to start with my molarity. 0.0350 moles of H2SO4 for 1 liter of H2SO4 times, and again, I need this in liters here, times 1.0000 liters of my H2SO4 solution. Again, that's putting this into liters. So 1,000 mils, and I had 4 zeros there, so 5 sig figs overall. I kept my 5 sig figs in my answer. If I stopped right here, let me turn this color into something that we can actually see. Okay, if I stop right here, this would give me my moles of my sulfuric acid, but that's not what I want. I want to know how much bicarb I can make, how much bicarb I'm going to need. I see from my balanced reaction that 2 moles of bicarbonate, sodium bicarbonate, I apologize. My mind is thinking bicarb, and then I'm not writing the full formula. 2 moles of sodium bicarbonate reacts with 1 mole of sulfuric acid. We need the grams here. So add that up. Sodium is 22.99 grams per mole. Hydrogen is 1.008 grams per mole. Carbon is 12.01. And oxygen is 16. And I have 3 of them. Again, remember, I always have a periodic table with you when you're looking these things up because it can really help you guys solve these problems. Great website is ptable.com. 84.01 grams of NaHCO3 for every 1 mole of NaHCO3. Calculate this out. This has 3 sig figs. This has 5. This is exact. This has 4 sig figs. So my final answer can only have 3 sig figs, and it comes out to 58.8 grams of sodium bicarbonate. So in order to neutralize 1 liter of a 0.35 molar sulfuric acid solution, I would need almost 60 grams of bicarbonate to do so. Okay, let's talk a little bit about an acid-base titration. An acid-base titration is a neutralization reaction. You have an acid reacting with a base to form salt plus water. Titration itself is a technique. A titration is a technique in which one solution of known composition is used to determine the composition of a second solution. Generally speaking, either the acid or the base in your system is a standardized solution. What that means is we know the concentration of that solution ahead of time. We use that known concentration to determine the concentration of the other solution that we need to find. Sometimes we're using solids to do this. Sometimes we need to use a standard to standardize something. We then need to titrate something else. So it may be a multi-step process we're doing here. At least one of the components here needs to be a strong electrolyte to let the reaction go. And a burette is the instrument we use to do this. A burette is a graduated instrument that's used to deliver specific, accurate volume measurements. Graduated just means that the marks are measured specifically to use to report those volumes, like a graduated cylinder, a graduated beaker. A burette is graduate marks. And you can see here in the picture, a lot of students have done this before, where they've taken a solution that's clear, and then they've added something to it, and they slowly see it turn pink over time. In this situation, this is an in color indicator called phenolphthalein. And under acidic conditions, it's clear. Under basic conditions, so an excess of base, it's pink. So you can see what we have is an acidic solution and we're adding hydroxide to it. Every time we add hydroxide to this piece, it neutralizes one of these little H pluses, forming water. So for every sodium hydroxide added, one water molecule is formed. And eventually the solution doesn't have any excess H plus anymore. We have an excess of hydroxide. The solution turns color and we can back calculate to figure out the concentration of the species we're interested in. So some important terminology here is titrant, equivalence point, endpoint, and indicator. The titrant is the solution of known concentration most of the time. It doesn't have to be known, but it's usually the known concentration. But your titrant is always the species that's in the burette, the burette. Okay. So sorry, I'm trying to turn off that function. Titrant is up here. Always, no exceptions. It's usually known, but it may be that we know the analyte and we're trying to standardize what's the titrant instead. We're usually using an Erlenmeyer flask for this, and your analyte is what's in the flask. We use Erlenmeyer flasks. They're really good for swirling your solutions without spilling them. We have endpoint and equivalence point. These are not the same thing, but they're hard to distinguish for students until you actually see this happening in lab. The whole point of the titration is to figure out what the concentration is of one of your species, your analyte or your titrant. So your endpoint is that point in the titration when the reaction is assumed to be complete, as shown by the indicator you are using, which is often a color change. It's often a chemical that will change color at a certain pH range. The endpoint, again, often involves a color change, and it needs to be as close to the equivalence point as possible. The equivalence point is what's most important. So equivalence point is more important than endpoint, but most often students are actually measuring the endpoint. Your equivalence point is the point in titration when the number of moles of titrant added is chemically equivalent to the number of moles of analyte. What I mean here is a stoichiometric equivalence, the point in the titration where enough titrant has been added to reach or to react exactly with the substance being analyzed. So the moles of titrant equal the moles of analyte. The reason I say it like that is if I'm mixing something like sulfuric acid with sodium hydroxide, this forms sodium sulfate and 2 moles of water. We need 2 moles of hydroxide for every 1 mole of sulfuric acid. So for every 1 mole of 1 mole of sulfuric acid in the system, I need 2 moles of sodium hydroxide. That is where it is chemically equivalent. And then the indicator is a chemical that changes color. Most often, that's what we're using is a chemical that will change color, and it's used to mark the end point of the titration. It's selected so that it changes color as closely as possible to the equivalence point we're interested in. Again, your endpoint means that you have passed your equivalence point. You've reacted all the acid you have in there. If you're titrating, and if your acid's down here, okay, you've added enough base that all of your acid has been reacted. Now the excess base that's being added is reacting with the color indicator in the solution, allowing that solution to turn color so you can tell it's done. When you see that color change, you've actually reached the endpoint. You're past the equivalence.